Good evening, everyone. If those of you who are here in the pavilion can put on your headphones so you can hear me. We're going ahead and getting started. And for those of you who are virtual, we're using something called a silent theater this time, and so I'm getting the headphones on the people here in the pavilion. My name is Pam Pearson. I'm the director of the International Cryosphere Climate Initiative. Good evening, good morning, good afternoon for those of you who are watching this around the world at the moment. This is the release here at COP30 of the State of the Cryosphere Report 2025, and thank you for joining us. As you'll see from the slide this year that is the cover of the report, we really wanted to emphasize the source and the impacts. In other words, you see here a calving iceberg and a flooding zone, and this is to make clear to policymakers here that there is this connection between ice and impacts, and that is something that we have been trying to emphasize for quite some time now with these reports. This really began in 2015 at the Paris Agreement with the Thresholds Report. We released a new update in 2019, and then starting in 2021 started this series of State of the Cryosphere reports simply because things are changing so quickly, and they're changing in two ways. One is the changes in observations, but the second that is really important for the future and climate ambition is the changes in projections and our better understanding of what is going to happen with the planet. Ice losses are accelerating, of course, and over the past 12 months, this just gives you a sense of some of the headlines that we needed to cover in this particular report. Weather and climate and ice loss are being supercharged in some ways by global heating. And these have huge impacts on ecosystems and communities around the world. And the reason for this is temperature. Globally, we're now at about 1.3 above pre-industrial. However, in the polar regions, this is much greater. This is the warming in the Arctic, which is 4 times the global average. Antarctica and the Hindu Kush Himalaya is 2 times the global average, and that's why we're losing ice in these regions. So I wanted to turn this over right now to the chief scientist of the Ambition on Melting Ice High-Level Group, Dr. James Kirkham, who will walk you through the findings of this year's report. James.
Thank you very much, Pam, and good evening to all of us of you here who are in Belém, Brazil, and also those of you who are online around the world. So what I'll do over the next 15 minutes or so is go through the major scientific updates which we covered in this report this year and their implications for policy. I'll then hand back to Pam to talk about what these mean for the negotiations happening here in Brazil. So one of the landmark papers published this year is an exercise called GLAMBI, which is a huge group of authors who came together to examine how much ice has already been lost from the world's glaciers over the last 2 decades or so. In the pie charts you're about to see in a second, the red segment show the amount of ice that has already been lost from these regions, and you can see it's already extremely substantial. So from high mountain Asia, we've seen nearly 9% of the ice lost in those glaciers over the last 2 decades. And then in the Arctic, we're talking about between about 3 and 7%. Scandinavia has already lost 14%. Iceland, 6%. Greenland, 7%. Arctic Canada South, 7%. Western Canada is extreme, 22%. Alaska, nearly 9% already as well. But some regions have lost substantially more, and even close to a third of their ice. So in the Caucasus and the Middle East, and in the Alps, really extreme losses of nearly 40% of their ice already lost over the last 2 decades or so. And in the southern Andes, that's about 12-13%. Now, all this ice loss is already having dramatic impacts, and we saw back in May the collapse of a glacier in Switzerland, which unfortunately buried the village of Blatten. Homes which had been occupied for centuries were wiped away in an instant. Luckily, there was no one killed in this exercise because they had swift evacuation, but these events are becoming more prominent all around the world and in many places where such evacuation information is not available currently. In Pakistan, elsewhere, glacier melt was amplified this year and combined with monsoon rains in the summer, releasing deadly flash floods that killed over 70 people. And another landmark piece of work featured in this report asked the question, how much ice will be left on the face of this Earth once temperatures fully stabilize and the glaciers have a chance to fully equilibrate to these over the coming decades and centuries? And actually, we brought the authors of this piece of research to SP62 in Bonn because of its relevance for these negotiations and the long-term temperature goal. Now, this research found some fairly shocking results, and that is that the regions you can see on this graph here, all of these will lose half of their ice with temperatures that are far lower than today. So the Rockies and Western Canada, once these glaciers fully equilibrate to the temperatures, half of that ice would have already been lost at 0.7 degrees above pre-industrial levels. Iceland is similar, below 1 degree, European Alps below 1 degree, Scandinavia is 1 degree, and the central and eastern parts of the Himalaya will lose half their ice committed at 1.2 degrees. Now, we're currently heading towards about 2.6 degrees of warming, and as we head towards nearly 3 degrees here, we'll see that many of these regions will lose their ice entirely or almost all of it. The picture really isn't much better at 2 degrees, with a bit of ice hanging on in the Rockies and Iceland and the European Alps, but Scandinavia will still lose all of its glacier ice at 2 degrees of warming once that fully plays out over the coming centuries. However, if we can bend the temperature curve down to about 1.5 degrees, we can make a true difference here, and these regions will still have some of their ice remaining once those glaciers fully adjust to those temperatures. If we then look at these other regions here, we can see the picture is similar but slightly better than today. So at 1.6 degrees, we see half the ice lost in the tropics and the Caucasus. Alaska will lose half the ice at 1.7, and Central Asia to the Western Himalayas, somewhere between close to 2 degrees. Now, at 3 degrees of warming, we see extreme losses still, which will have enormous impacts on downstream communities, hydroelectric power generation, water supply, as well as the incidence of extreme events and floods. Again, the picture is slightly better at 2 degrees, but really we need to be aiming again for 1.5 degrees, where we can make a real difference here in terms of the amount of ice left. And the key headline from this paper was that by limiting warming to 1.5 degrees, we can save twice as much ice globally compared to our current trajectory, and up to 25 times as much ice in some regions. Now, moving on to our enormous ice sheets in the world, we have Greenland and Antarctica, and I've overlaid a map of Europe here on top of Antarctica to give an idea of just the scale of this huge place. So if those of you from Europe here, please find your country, and then imagine the country covered by about 4 kilometers of ice in places. Then you get a scale about how vast these places are and the amount of sea level rise they could unleash upon the world in the future. For our Brazilian audience here, I've also compared that to Brazil. So Antarctica is still bigger than Brazil, which is an enormous country, as many of us can appreciate flying over the Amazon on the way to Belém. Now, our ice sheets have been responding increasingly to a warming Earth over the last 3 or 4 decades or so. And so these animations here show in red areas where ice is being lost and is not being replenished. The numbers on those ice sheets show how much ice is locked up in them. So if a Greenland were to melt, sea levels would rise globally by about 7 meters. West Antarctic ice sheet 5, and East Antarctica, a giant, nearly 60 meters. Losses have quadrupled since the 1990s. Another one of the landmark papers published this year was published by Chris Stokes, who's one of our authors and will be on a panel later. And they looked at what is the safe long-term limit for ice sheets. And they concluded with a statement which is becoming an increasingly consensus statement within the ice sheet community here, which is that 1.5 degrees is really considered far too high for ice sheets. And even our current temperatures, if we stay there for long enough, will lead to extensive loss and damage because of irreversible sea level rise being locked in on the Earth. They conclude that avoiding these irreversible damages requires a global mean temperature lower than today's levels. So really, we're talking about 1.5 and 2 degrees here at COP30, but we should be thinking much further into the future and much lower temperatures to stabilize losses from our ice sheets. Now, these findings were backed up by the Global Tipping Points report published about a month ago. And they concluded that if you were to have a precautionary principle approach for the ice sheets, so reducing risk that these will be tipped, we really need to be aiming for around 1 degree or even below that level in the long term to prevent up to 10 meters of devastating sea level rise being unlocked and unleashed upon the world over the coming centuries and millennia. Elsewhere, another important paper simulated Antarctica's response to past warming and cooling cycles, and they found that a tipping point might be crossed with even potentially just 0.25 degrees of further ocean warming. So what you can see here is the response of the ice sheet over the last 800,000 years, and this dotted line here is our current ocean temperatures. And what you can see is that once this is exceeded by even a small amount in a second, we see dramatic losses in the ice sheet again and again and again. So this paper really warns of the irreversible damage we're locking in with very little further climate warming and ocean warming in the future. The report also highlights how surface meltwater is rapidly increasing across the surface of Earth ice sheets, particularly in East Antarctica, which has become a melt hotspot over the last 2 decades. And these observations, alongside other ones in terms of annual surface temperatures, glacier velocities, ice sheet mass loss, and ice shelf area, have led some authors to conclude that Antarctic climate processes are actually behaving increasingly like those we see in Greenland, a process they call the Greenlandification of Antarctica. A number of other scientific advances are also listed in this report, which highlights processes and new observations that need to be more accurately presented in ice sheet models if we are to reliably predict sea level rise in the future. Some highlights include the role of fracturing within Antarctic ice shelves, the importance of subglacial water within models, and also the shape of the seafloor surrounding the continent and the ice shelves, which bring those warm waters in to melt the base of those ice shelves. Another prominent paper assessed the prospect and the viability of polar geoengineering concepts, which have seen increasingly proposed as an alternative solution or a complementary approach to climate action here at COPs in the last few years. We had a large group of over 40 world-leading polar and climate scientists here, objectively assessing the 5 or 6 most prominent polar geoengineering proposals that have been found in the literature over the few years. And the conclusions are they found none of these ideas provide a viable and responsible way of limiting climate harm to the polar regions and their worldwide implications. Instead, they found that these proposed interventions would be environmentally dangerous and come with a huge risk of ethical and large governance challenges alongside grave unforeseen consequences. And of course, the robust environmental protections already in place for the polar regions would reject these polar geoengineering ideas. The authors conclude that these are not the way to minimize the harm to the polar regions, and instead we need to focus on decarbonizing, protecting them through marine protected areas, and specifically in terms of Antarctica, specially protected areas, rather than trying to attempt these speculative interventions that would very much likely not work. Moving on to polar sea ice now, which, as we know, plays an incredibly important role in cooling the Earth by reflecting all that solar energy back out to space. Sea ice has been declining at both poles over the last few decades, and especially in Antarctica in the last decade, losses have been extremely concerning. So in February this year, the global extent of sea ice reached a new record low, as you see on the left of this plot here. And whilst Arctic sea ice decline, which you can see on this graph here, has been pretty consistent in its downward trend over the last 40 or more years or so. In the last decade, we've seen really concerning signs of change in Antarctic sea ice. And in fact, when you split this down to the winter sea ice extent and the summer extent, we can see that Antarctic sea ice has lost around the same amount of sea ice as the Arctic in the last decade, but over a rate that is 4 times as fast and almost twice as fast in the summer. So now there's always been a lot of talk and speculation about when will be the first ice-free year in the Arctic, because it's an incredibly symbolic event. But given actually that you can see that in the summer in Antarctica, in this blue line here, there's actually less sea ice. So given that this rate of decline is even sharper than the Arctic, we might see the first ice-free year for sea ice globally occur in the Antarctic before the Arctic, given this steep rate of decline. Now, the current decline of sea ice at both poles now means that its reflective cooling effect has reduced by about 14% since the 1980s, and this will have profound effects on enhancing summer ocean heat uptake, amplifying the warming of these regions, and of course contributing to more extreme weather around the world. But there still is hope, and there is great mitigation difference between our current emissions and a more optimistic and ambitious emissions pathway that you can see here. With our current pledges in place, on the top row, the Arctic Ocean will lose its permanent sea ice cover for several months a year. This will be like putting a radiator next to the Greenland ice sheet and most of the permafrost in the world. But with ambitious mitigation here at COP30 and in the coming years, Arctic summer sea ice can maintain around the record low conditions first experienced in 2012, although we are still likely to see ice-free September extents within the next 3 decades and potentially as close as 2030, even with the low emissions. Moving on to permafrost, which covers a vast area of the Arctic. For those of you who are here in person, we have Permafrost Day tomorrow in the pavilion, so come along for more information on this. But once this vital store of carbon thaws, it releases more and more emissions to the atmosphere, which cannot be stopped for centuries. And when we talk about permafrost to policymakers, we often talk about the country of permafrost, because emissions, even today, equate to a top 20 emitter, so around the size of Japan's today. Now, if we can limit warming to 1.5 degrees, emissions will grow to roughly the size of India's today every single year over the coming centuries. And by 2 degrees, this will grow as large as the EU's. Beyond 3 degrees, this really becomes one of the top emitters of the world, so China or the US, through to 2100 every single year. So a significant problem eroding that remaining carbon budget we have to hit those key climate targets. Now, at least 30% of the Arctic's land ecosystems are now a net source of emissions, and of course greater and greater areas are becoming sources of emissions as temperatures rise further. And as well as those emissions, permafrost thaw threatens the homes, livelihoods, and cultural heritage of over 3 million people living in the Arctic today. In Alaska alone, this will cost between, well, definitely billions, but we have a choice between a few tens of billions or up to $50 billion over the coming decades. So enormously challenging amounts of money to adapt to this continued thaw of permafrost. Elsewhere, polar ocean acidity has now reached critical levels, and this was confirmed by a planetary boundary paper that, especially in the Arctic and the North Atlantic, polar ocean acidification has now crossed the planetary boundary. This reduces suitable habitats for keystone shell-building species that are vital components of marine food webs. And another series of results that are highlighted in this report look really concerning long-term projections of ocean circulation decline, such as the AMOC, and also in Antarctica, the Antarctic Circumpolar Current. For the AMOC, researchers estimated that with high emissions, by about 2100, we'll be seeing about 70% of those simulations showing a risk that AMOC is slowing down. But this can be decreased significantly by intermediate and low emissions, so it's really critical that we can reduce our emissions as quickly as possible to limit the risk that we'll be hitting these really dangerous tipping elements of the Earth system. Around Antarctica as well, researchers have also forecast about 20% weakening of the Antarctic Circumpolar Current, even by 2050 if today's emissions continue, largely driven by ice sheet mass losses. And as the oceans are massively connected throughout the world, a weakening of this critical current would reverberate through the global ocean system. So Before I pass back on to Pam, I want to really conclude with 5 or 6 of the really key science updates from this year and the most policy relevant ones we want to highlight here at COP30. Firstly, substantial glacier loss is occurring even at current temperatures and impacts are escalating worldwide. 1.5 degrees in the long run will save twice as much glacier ice globally and up to 25 times more in some regions compared to our current emissions. This is going to be crucial for making adaptation possible. However, 1.5 degrees and even our current temperatures of 1.2 degrees is far too high really to prevent loss and damage from polar ice sheets. So we should be aiming in our minds about thinking of how do we bend that curve downwards and go 1 degree or below in the long run. And this has been confirmed by tipping point analysis, which really shows that risks need to be, we'd be looking at this 1 degree temperature goal, really rather than the 1.5 degree temperature goal. And of course, we're seeing escalating changes to Antarctic sea ice and polar oceans. And so with that, I'll pass back on to Pam for a general outlook on the policy here and what we think the solutions are at COP30.
Thank you so much, James. And this is a real gallop through all of these different kinds of dynamics. And over the course of the next 10 days of this COP, of course, we're going to be delving deeper into some of these dynamics going forward. But what does it mean for the negotiations? Because that's really what this is about. Sometimes there's a myth going on that, all of the talks has had no real impact. And as this graph shows, if we had not had the Paris Agreement, this is where we were headed, right, into this red zone. So there has been an impact. We have sort of evened out. We're moving downwards. If we take all of the pledges that have come in to date now, including through 2035, we do see about a 12% decrease in emissions by 2035. The problem is that according to the 1.5 degree report that came out already in 2018, we should be seeing a 43% decrease by 2030 and much more of that by 2035. So we're very much off track to where we need to go. And the UNEP emissions gap report came out last week and just today here in Belém, the climate action tracker. And it's fairly depressing reading. Really, de facto, there's been no change from last year to this year. We're still kind of on track for 2.6 degrees. If you look at it from the most ambitious point of view, there was about 1/10 of a degree decrease on a couple of these measures. Most of that was actually methodological, and so from a statistical point of view, no change from last year to this year. And as a matter of fact, if you look at pledges and targets, because of the withdrawal of the U.S. from the Paris Agreement, that has gone up by 1/10 of a degree from 2.1 to 2.2 degrees. And the most optimistic scenario, median warming, is 1.9 degrees C. And as you just heard from James, that is far too high. 1.5 over time is too high. And so we're nowhere near on track to where we need to be. Instead, this is what we need to do in terms of NDCs for the cryosphere. And last week, Climate Analytics and Potsdam Institute released what they call now highest ambition pathways. And these are able to bring us down back below 1.5 degrees by the end of this century. And if we continue these kinds of measures, they would bring us to below 1 degree by 2150, which at a minimum would very much slow a lot of the dynamics that we're talking about. But this requires really intense action going forward. We need to start reducing our carbon emissions now in 2025. We need to reduce them much more quickly because of the time that we've lost. And we need to be pulling carbon out of the atmosphere in order to really bring temperatures down again. It is a bit of a myth sometimes that there's built-in warming in the system, and that, we're going to continue to see warming for some time after CO2 levels begin to drop. But the reality is that once CO2 comes down, temperatures follow pretty quickly afterwards. But what it requires is a phase out of fossil fuels, with coal in the 2040s, gas in the 2050s, oil in the 2060s. We need to halt and reverse deforestation. We need to also cut back on what are called the short-lived climate forcers and close to cryosphere regions. That really includes black carbon as well as methane. And again, we need to scale up sustainable carbon dioxide removal methods for temperature decline afterwards. Sorry. And we can do this because of the radical expansion that we've been seeing over the past 5 years, in particular in renewables, where wind and solar can really begin to replace the fossil fuels that are causing us so much problems right now. And again, we can reach 1 degree or below by 2150. At that point, what we're going to be able to see is some degree of reversal in places like glaciers, for example, where if we're following these pathways, we'll see them begin to stabilize by the 2060s or 2070s, and maybe even by 2150, a bit of regrowth. And so it is actually a message of hope, but also a message of urgency. And we're not really seeing that urgency necessarily here at COP30 right now. And in some degrees, there's been a little bit of a loss of momentum for 1.5 degrees, and that is not the time that this needs to take place. If you could advance the slide, please. Seems to have, here we go. So I wanted to say a thank you for this report to our scientific reviewers. Some of them are in the audience right now. We're going to call them up for the Q&A. But really, this is a massive effort, and we really appreciate the work that they've done. We need to be going, there we go. Okay, and here, if you want to download the report, there's a QR code. We hope to have also paper copies of the report available relatively soon. So if I could now, I'd like to ask for the reviewers in the audience to come up and sit on our panel. This is Chris Stokes for ice sheets, Gustav Hugelius on permafrost, Höjes Landtweet, who just arrived after a long journey from Germany, from Avi, and Miriam Jackson, a glaciologist, and then we'll have James up here as well. And we're happy to take your questions. And I'll try and move out of the static area. I hope you guys aren't getting the feedback that I am. I don't know who's running the microphone right now. Andres from Chile is running the microphone. So if there are questions, please just raise your hands. Okay, Ellie, please.
Yes, hello. I'm Professor Matti Kuittinen from Aalto University, Finland. 2 questions, actually. First, about the loss of ice sheets and glaciers if we have overshoot. So how does the length of the overshoot respond to the probable sort of like loss of ice sheets or the recovery or their recovery? And then the second question is about what we need to be doing. You showed that we would need to scale up land-based CDRs. Why land-based? Why only land-based? Aren't all CDRs important? Thanks.
Okay. Anyone wanting to take those?
So I'm happy to take the first question about the ice sheets and for how long we can stay in that kind of overshoot scenario. I think that the simple message from ice sheets is that every single fraction of a degree really matters. And so I'm getting some interference here, but yeah, so the higher you go and the longer you sustain it, the worse the effects. Most research shows that you might be able to cope with limited overshoot of a few decades. Certainly with the Greenland ice sheet, there's some research showing actually you can reverse it quite quickly if you don't go for too long. But with Antarctica, the problem is that they're highly non-linear. So even a small nudge in the climate, a fraction of a degree, could tip them into a state that then becomes irreversible, at least over human timescales. So the longer we go over 1.5 and the higher we go, the more dangerous things are and the more risks we're taking.
And the overshoot that the highest possible ambition, the most ambitious pathways, assume an overshoot now that is probably unavoidable of 1.7 to 1.8 degrees for 30 to 40 years. We're going to be having a side event on geoengineering next week, but just to sort of summarize, the climate analytics and Potsdam emphasis was on the feasible CDR that we have right now, and right now marine CDR just isn't there yet. So that's why it's and we even say sustainable CDR, of course, because you have some land-based methods that would not be necessarily sustainable, or using huge tracts, or only occur on indigenous lands. So there are a lot of issues with that, but these need to be taken into account as well. Other questions? Okay, oh yeah.
Sorry, a follow-up question then about the likeliness of the fading of amok. You showed that it would be 25% even with a low emission scenario by the end of the ongoing century. Now, just this year, Jim Skia, the chair of IPCC, visited our country, and he said that amok is not going to fade away. So what is the consensus in these discussions that you are having? Because some of my fellow professors of meteorology, they say that it's going to take thousands of years. And because I'm not an expert, I'm reading reports that are very alarming, and then some guys are saying that no, don't care about it. It takes millennia anyway. So where are we in the consensus, or is it possible to reach a consensus before we are too late?
Anybody want to take that, or you want me to? James? Yeah.
Yeah, you're absolutely right. In terms of, there's a very large spread of models still out there in terms of AMOC, and the pace that it slows down is still skeptical. I think what I would say is that compared to a few decades ago, I think the way the research is now pointing is that it's probably more sensitive than they used to think it was, which is then warranting a lot more research into exactly trying to figure out how sensitive that is, how quickly it could slow down or collapse, for example. And I think given the enormous risk to countries like yours from this collapse, it clearly shows we need to be doing a lot more to do more research into this, constrain those uncertainties and the likelihoods in the future. I believe we have a dedicated side event about AMOC next week, is that correct? So, and Stefan Ramstorff, who is a much more qualified person to speak about that than I am, will be speaking there. So perhaps you can come along and get some more details out of that.
And I know one of the things that Stefan would say and will be saying is that one of the reasons there is that large spread of uncertainty is because our observation period for these ocean currents is relatively short. It's really only about 20 years. So the models are trying to match 20 years of decline, unfortunately, but there's also a sense that we just can't be sure that, it's going to continue to track. So that's part of the problem.
Hello, my name is Fabian Seemann from the Alfred Wegener Institute in Potsdam, Germany, and I have a question on the state of permafrost and geoengineering. Are there any, like James presented the report on geoengineering in polar regions, are there any geoengineering ideas that concern permafrost that would be feasible, or is it a similar picture as the scenarios that James presented? How would you guess that?
Thank you. I would say that given the size and remoteness of the permafrost region, it's roughly 15 million square kilometers, largely uninhabited land. There really are no feasible direct interventions that you can apply to permafrost regions that would make a broad-scale meaningful difference. There are basically two things two management-based strategies you can do to reduce permafrost thaw. One of them would be to manage fires more intensely, to put out forest fires more intensely, even when they don't occur near habited places, which could be implemented in both North America and Russia. Currently, forest fires on permafrost are often left to burn, which leads to large-scale permafrost loss over time. And another thing that you can do, which is very much more local, is that you can, in the winter time, if you remove snow where you have infrastructure from houses or from railroads, etc., you just remove the snow and let the cold air penetrate into the ground. You can actually save the permafrost locally. So this can be done within a single community or so around housing, but it's not a broad-scale implementation that you can do across large areas. I think those are the main feasible and geoengineering or management type scenarios that you can apply.
Yeah, maybe to follow up on what Gustav said, I think there are some very concrete examples of the usefulness of that approach of removing the snow, for instance, with ice cellars. In communities in the north, you can actually target it where some of these ice cellars were created 100 years ago and then are made of wood or wooden structure that are embedded in permafrost that it is really warming very strongly. And there, if you do actually remove the snow, you can have like some direct achievements. So there are very direct applications to it. One thing that we've heard very often about the permafrost is actually to use the revival of places in animals and to bring them on permafrost. And the idea behind that is obviously to have like the large mammoth to tramp the vegetation. And by having that effect, you would change the thermal conditions of the ground and then you would contribute to preserve the permafrost. This is a very nice idea, and actually we had a PhD student recently finished his PhD on that, and you see that there are actually mixed results. There are some in specific settings, at specific locations, you might achieve that effect, but over large areas this is much more difficult to manage and to implement, and specifically because the landscape is so diverse in the permafrost region. It might not look like that when you are from abroad on a satellite image, but you have lakes everywhere, so many lakes in the permafrost region, so you won't be able to achieve that much with that approach.
Although it would be kind of cool to see mammoths. Yeah.
Hello everyone, I'm Josep, I'm researcher and teaching fellow from the University of Barcelona. I have two questions. The first one is, what do you think about this group of people that do not believe in the science, which is quite clear about climate change? If you have any message to give to them. And the second question is about your experience with in the climate negotiations. Do you feel that the politicians are listening to you and they are applying the policies that seem more effective to reduce climate change? And if you have observed changes in the last years since in the last decades? Thank you.
I can answer the first one. One of the good things about the cryosphere is that it shows you what's happening with the climate. If you talk about the increase in carbon dioxide, it's gone up a lot in my lifetime, and to be honest, I haven't noticed that at all. You don't notice the carbon dioxide. Temperature as well. We know that the average temperature is increasing, but when you get a cold winter day, it doesn't feel like it's increasing. And when you talk about 1.5 degrees compared with 3 degrees, you know, these aren't things that really affect how you dress to go out or what you do. These are very small changes. But if you look at, for example, at glaciers, at mountain glaciers, you know, just this small increase has a huge effect on glaciers. And you can see that. You can see a glacier, how it looks now and how it looked 20 years ago. So I think these are one of the modes of communication we have to use with people that don't understand. You know, that say, well, you know, it doesn't feel like it's getting warmer because it's really cold today, that look what's happening to the glaciers. This is our record. This is the best evidence we have of long-term climate change. And I'll let someone else answer the second question, but just say that I think a lot of people think things like permafrost and changes in sea ice are regional effects. And this is something that I think still some of the policymakers don't understand, that changes in sea ice, you know, who does that affect? Alaska, Canada? No, it affects everybody. You know, this affects the albedo of the Earth, so it's global. And this is something that we're still working to make policymakers understand, and possibly James or someone else wants to follow up.
Thanks, Miriam. I hope you can hear me in the audience above the sound of this lovely concert we're having behind us. So just to follow up on that, I think it's also really important to distinguish that those of us often from the north of the world or Western Europe, for example, may not notice this temperature difference, but in my own experience, the most moving testimonies of climate change impacts today have come from youth in least developed or island states. And I can vividly remember last year in Baku listening to a youth delegate from a small island state speaking about how she couldn't grow the food they used to grow up with because sea level was rising too much. They couldn't use the wells in their communities anymore because they'd been poisoned by salt water slowly encroaching into their lands because of this rising sea level, which is driven at an accelerating pace by the loss of our glaciers and ice sheets. Now, on your second point about what we're seeing here at COP30, I think that more than ever before we're seeing a coordinated pushback on science, particularly by the usual suspects, but they're more coordinated than before, and they're challenging the authority and the use of, say, IPCC as best available science here, as well as myths and methodologies about overshoot of 1.5 in the Paris Agreement. Now, even if we temporarily overshoot 1.5 degrees, that remains the legal, moral imperative for our efforts, and we can approach 1.5 degrees from either below it or above it through overshoot. This has to remain our number one priority, and of course this was confirmed by the advisory opinion of the International Court of Justice earlier this year. I think what we have to do, and it's not all countries, and there are definitely encouraging signs, such as even today within the research and systematic observation negotiating track from countries like blocks like the EU, AOSIS, the least developed countries, coming back and reaffirming the absolute critical, essential importance of the IPCC as best available science, and that science must guide this process going through all these negotiations, but especially in the run-up to the second GST in 2028. Pam, you want to add to that?
Thank you. And I'd say also that tomorrow at 3 p.m. there will be a UNFCCC side event where we're among the co-organizers that is actually going to be addressing this attack on science. We'll have both scientists there. James and Chris will both be speaking. Also Bill Hare, who's one of the key people behind these new highly ambitious pathways. And countries who are negotiating right now about this pushback on science and how they're trying to manage that right now. But you can definitely see it, and it is, kind of an indication perhaps that governments, on one level, that the message is beginning to get through precisely because they're pushing back on it so hard. They're trying to remove references to cryosphere, for example. A very classic one that has bugged me for years is that many of these decision points will talk about slow onset, high impact events. That's sea level rise from ice sheets. It makes a lot more sense to say that as opposed to use euphemisms to refer to them because, especially the general public, but even politicians and policymakers don't understand that. So part of what I would say the scientific community and some of these country groups like AOSIS, the Environmental Integrity Group, which is mainly mountain countries, and so on, they're really trying to put this plain language into the decisions so that it's understood exactly what is being talked about here, so that we can't avoid the reality. We had a very good meeting today with some visiting parliamentarians, and the analogy that was used, which really spoke to them, is the analogy almost of someone with cancer. And I'm sure all of us have had a relative who has suffered from cancer, been told by the doctor that this is what you've got to do. It's chemotherapy, you feel okay right now, but if you don't do anything, you're going to be suffering over the long term. And that's exactly what we're looking at right now. You may not see what's happening in the cryosphere because you live very far away from it, but what these scientists are trying to say is that it is happening, it's going to have global impacts, and we need to act on it right now to prevent these really, really catastrophic impacts in the future. So with that, I think we're about out of time. We thank you for staying so late. If there are urgent questions, we're happy to take one more. There is one. Okay, please, go ahead.
Victoria Hochlova, Hafen City University, Hamburg. I'm from another perspective, from urban planning, and here I'm trying to connect actually science and when real from the cryosphere places with the settlements, their governors who have to act. My question is, you partly already answered it, James, speaking about the sea level rise and how it affects, but the question is about the extreme weather events and whether you are able to track it and to couple places in the world, in some countries, with some places in the cryosphere. Are you able to track it precisely and say that if in Arctic, for example, in specific place, the temperature will rise or we're going to lose another glacier or another iceberg, then in particular this land, there will be tsunami, droughts, wildfires. Are you able to make this coupling so that it kind of gain even more attention from the governors of other countries who seem to think that they are super far away from the cryosphere and they don't understand this connection?
I think linking it to particular places is difficult, but there have been attribution studies done in recent years, and it's getting stronger and stronger. And what they've shown is that the sea level rise we've already had because of fossil fuel burning and pollution is adding billions of dollars onto the cost of every single storm. And this will only continue to accelerate throughout the years. I mean, within my own lifetime, the rate of sea level rise has already doubled, and it will increase extreme weather events. And of course, we talk about the long-term inundation of cities, countries by rising seas, but the real near-term damage is going to be exacerbating those extreme weather events and the damages they cause. And so what we'll go from is nuisance flooding initially as the sea level rises more and more with high tides or storm surges, and they'll become so frequent that things will become very hard to adapt to and inhabit. And as we heard from Chris's analysis, as we continue to rise, if this acceleration in current sea level rise continues, we'll be reaching rates of sea level rise by the end of this century, which are, the IPCC has said, will be very hard to adapt to for adaptation measures, which is just another message of why we need to get a handle on this immediately this year and continue to reduce emissions going forward over the coming decades as quickly as possible. Anyone else want to add to that?
Thank you, James. Briefly, as we speak now, we are submitting a paper on the circumarctic risk from floods, from storm surges, exactly what James mentioned. What is really interesting about it is that in conducting those analyses, and I could quote a lot of them in the panel, is that we're starting to link a lot of these cryosphere components that traditionally had been considered in isolation. So we're linking sea ice, mostly fetch, and a lot of component there in assessing the vulnerability. By doing so, you can start to actually attribute some of the factors. It remains fairly rough at first in an estimation, but you can start to do that. And it differs quite a bit depending on where you are in the Arctic, whether you are in an open ocean in the Beaufort Sea or a place where you have a lot of permanent sea ice that might disappear in the near future. So I think there is a lot of promises, scientific promises, to identify some of these factors that are behind it there. And maybe the last thing I wanted to say is that that maybe in reference to your question and the twist of things is that I work with a community in the Arctic since 20 years, affected by floods and erosion. That is the main concern that is identified by the community. And surprisingly, in that location, you would expect the voters, or traditionally the voters, have been voting on the side of what you are describing, those skeptics, or sharing some of these values. But there is a very strong discrepancy actually between the concerns on site and the reality of climate change, the fact that people do not deny it at all, and those values that are there. And I think that's the beauty of things, and maybe the message of hope is that ultimately when reality strikes, then you can't really deny it. And that's really true in the Arctic. You see it with your own eyes.
I'd say also with the special report on cities especially, think of how many megacities we have that are coastal. And so it really is a very large population. But I wanted to give Miriam a chance also to talk about cities that are dependent on mountain water resources, and they may be hundreds or even thousands of miles downstream.
Thank you, Pam. I was hoping to jump in there. There are several cities around the world, and especially in high mountain Asia, where they do get a significant amount of their water supply from glacier melt or snow melt, or a combination of both. And it could actually be a fairly small proportion, but it could be very important in hot and dry periods of the year. And of course, when it's hot is when you get the most glacier melt. So even though it might not be a big component of the total water supply, it could be very important. Another one else when you talk about urban planning is I've just come back last year from Kathmandu. I spent several years living in Kathmandu, which was brilliant, but also a lot of challenges in terms of air pollution, electricity supply, water supply. But not long after I moved there, the water supply was solved. They had this water supply from Malamchi and everything was brilliant. And then about a few months after that was turned on, there was actually sort of some cascading hazards. It was a glacier lake outburst flood linked to a landslide, linked also to intense precipitation. But at least some of the components were cryosphere related. And suddenly, that was, the Malamchi water supply was just gone. There was a lot of devastation. And this is a city of several million people. And, some, to be honest, relatively small changes in the cryosphere had this huge impact and affected the water supply for millions of people. So we think the cryosphere is a long way from urban areas, but in some parts of the world like Kathmandu, it does have a big effect.
All right, thank you very much, everyone. We appreciate the questions and the engagement, and thank you. I'd like to give a round of applause to our wonderful reviewers. We have one more back there, Christina Shadle, who came in late, so I did make her sit in one of the hot seats, also on permafrost. And tomorrow will be Permafrost Day here in the pavilion, and so we're looking forward to hearing more about that. So thank you, everyone. Have a good night and safe journeys to wherever you're headed, and thank you to those online.